Hey, pre-calculus. So I'm going to label these notes 7.4 inverse trig functions. And for this first bit, you don't need to copy these graphs down. Just listen. What I do want you to copy down are the orange boxes. So make sure you get these written down. If you want to copy the graphs, feel free, but if you just want to listen and absorb, that's okay with me too. So the reason I put these graphs down is if we look at the graph of sine of x, we get this nice wave. The only problem with this guy is that it doesn't pass the horizontal line test. And so when we're thinking about inverses, for a function to have an inverse, it has to pass the horizontal line test. So we can't really say that this function, the sine function, has an inverse unless we do something to the domain. So what we do is we restrict the domain, meaning we're going to just look at a teeny little tiny part of the graph and we're going to ignore everything else. So for sine, the part that we look at is from negative pi over 2 to pi over 2, or negative 90 to 90, right? So we cut the graph down to just that bit. And when it's this little teeny piece of the graph, then it does pass the horizontal line test. Now, what the inverse function is going to look like is the same little bit of curve, but reflected over the line y equals x. So notice that like this point right here is the point over pi over 2 up 1. Right? So then over here, if I flip the x and the y, if I switch them, I have this point that's over 1 up pi over 2. So recall that I get my inverse function by switching the x's and the y's. Okay, now we do the same restriction game with cosine, but cosine, we don't want to restrict from negative pi over 2 to pi over 2 because if we restrict it there like we did for sine, we still wouldn't pass the horizontal line test. A bunch of horizontal lines, in fact, most of them, would cross twice. And so instead with cosine, we're going to restrict it from 0 to pi, or from 0 to 180 degrees. So that's the little piece of the curve we're going to restrict to. And then again, if I switch all of my x's and my y's, my inverse function is going to be this little chunk of graph right here. And notice that, for instance, like I've got this point over pi down 1. And when I flip that, I'm going to get the point negative 1. So I go back 1 up pi. So that point is right there for the inverse. Lastly, with tangent, tangent doesn't escape this horizontal line test problem. Pretty much any horizontal line, in fact, every horizontal line with tangent is going to hit the graph. And so again, we have to restrict it to one piece of the tangent curve. So here we're going to go negative pi over 2 to pi over 2, or negative 90 to 90, which is what this says right here. And then again, if you just want to see what the tangent inverse looks like, we're going to switch all of our x-y pairs. So when we switch x and y, that means our vertical asymptote becomes a horizontal one. Vertical asymptote becomes horizontal. I actually think I switched. This is the negative one, so here's my negative. This is the positive asymptote, so here's the positive. And then you switch all your points. So for instance, 0, 0 stays at 0, 0, but this is now over 1 up pi over 2, where it was, sorry, pi over 4, I think, where it was over pi over 4 and up 1. So they switch. For the purposes of your notes, though, you really just have to have the boxes written down. That's the main thing that you'll need to know to go forward. All right, so now things to add to your notes. Let's take a look at a first example. Evaluating inverse functions. When it says evaluate, that typically means find the answer. And for us, it's usually going to mean to find the exact answer, which means using your unit circle. So what I want to see for problems like this for your notes is I want to see you draw a little unit circle. Okay. And then on the unit circle, you need to think about where sine is negative. Now recall that sine means we're going up and down because sine is the y value. And since it's negative, it means we had to go down. So we're either down in this quadrant a half, or we're down in this quadrant a half. Since sine has to be, the inverse sine is between negative pi over 2 and pi over 2, or negative 90 and 90, the sine curve is only going to happen, or your sine inverse is only going to happen on this piece of the unit circle, only in quadrant 1 and quadrant 4. So that tells us that we're working in quadrant 4 with this point here. And since that's down a half, it means we went over root 3 over 2. So this triangle we're working with went over more than it went down. If it went over more than it went down, then I know this is the 30-degree angle. So this would be equal to negative 30 degrees Or you could say equal to negative pi over 6 if you were going to give your answer in radians. To look at another example of this, if we were doing cosine inverse of negative root 2 over 2, again, you're going to draw your unit circle as a way to show your work. Negative root 2 over 2, let's see, cosine I know is sideways. It's how far I go over, how far I go back, which means I would have had to gone back root 2 over 2. So I'm either in quadrant 2 or in quadrant 3. But based on our restrictions about where the inverse function is, it's either between 0 and pi. That means that we're only working with quadrants 1 and 2 of the unit circle. This is the only place where my inverse function lives. So it has to be this one in quadrant 2. This is where you went back root 2 over 2 and up root 2 over 2. So that means I'm 45 degrees away from 180. I'm also 45 degrees away from 90. And so that would mean that my answer for this would be 135 degrees. Or that would be the same as 1, 2, 3 pi over 4 radians. Okay. Now, tangent, root 3 over 3 isn't one of the nice places on our unit circle. It's a sort of combination of places on our unit circle. And so to get root 3 over 3, what would have had to have happened is that I would have had to have 1/2 divided by root 3 over 2. And then dividing fractions is easy as pie. You flip the bottom and multiply. That would have put the root 3 on the bottom. And then when I rationalize 1 over root 3, that's how I would get root 3 over 3. So this is coming from when the sine function is 1/2 and cosine is root 3 over 2, because I know that tangent is sine over cosine. So now that I've done a little preliminary thinking about this, I'm going to draw my unit circle. Since tangent is positive, I know I'm in quadrant 1 or quadrant 3, and because of the restriction, I know I have to be in quadrant 1. Let's see, if sine is 1/2 and cosine is root 3 over 2, that means I went over more than I went up, which means I'm at 30 degrees or pi over 6. Okay? And then finally, cosine of root 2. Now, this one is kind of sneaky because root 2, you can't really get with your root 2 over 2s for cosine. And we know this because if I take a look at root 2, let's see, the square root of 1 is 1. And the square root of 4 is 2. So I know that root 2 is somewhere between 1 and 2. But I also know that cosine, the biggest that cosine can get is 1 for my graph up here. If I'm looking at the cosine graph, the highest it ever gets is 1, and I also know that from the unit circle. So this is asking me, where is cosine bigger than 1? Well, the answer is nowhere. This is impossible, and so you would say it's undefined. So you have to watch out. Go ahead and put that in your notes. Watch out for cosine inverse and sine inverse greater than 1, because you can't do that. It's not going to be possible. If this thing in here is bigger than 1, it's always going to be undefined. Let's take a look at some new examples. These are ones that you haven't seen in class. So we have a composition of two trig functions, a trig function and its inverse. In this case, an inverse function is always equal to an angle. Notice that our answers from before were always angles. Negative 30 degrees, 135, right? So this inverse function is really a theta, which means what they really want me to find is the cosine of theta. And now I use this inverse to draw a triangle. So I have a right triangle, I label one of the angles theta, and then I know that sine is opposite over hypotenuse, so 3 here and 5 here. I recognize that this is a 3, 4, 5 right triangle, and then since this inverse function is equal to this theta, when I take the cosine of theta, I get 4 over 5. So my answer for this problem is 4/5. I can do the same thing with just an x. So here I'm finding the sine, and this inverse function inside here is equal to theta. Then I draw a triangle, label my angle theta. Cosine is adjacent over hypotenuse, and since there's nothing underneath this, I'm going to assume it's a 1. So my adjacent side is x and my hypotenuse is 1. I can use the Pythagorean theorem, x squared plus b squared equals 1 squared. That means b squared equals 1 minus x squared, which means b equals the square root of 1 minus x squared to find this opposite side. And now I want to find the sine of theta, which means I'm going to do opposite over hypotenuse, which is the square root of 1 minus x squared over 1. And we know that anything divided by 1 is itself, so my answer would be the square root of 1 minus x squared. And finally, we can have a composition with a double angle formula. So notice here you have sine of 2 times something. Anytime you have a 2 in the parentheses, it's going to be your double angle formula. So you turn this inverse function into a theta. You say sine of 2 theta. And then again, you come off to the side and you draw your triangle. So cosine is adjacent over hypotenuse. Since we just did the same triangle above, I already know that this is 1 minus x squared. And then I'm going to have to use my double angle formula to expand. So 2 sine x cosine x. And then once I do that, I look at this triangle. Oh, sorry, not x's. Bad, Mrs. Lowney. Thetas. This is where you have to be careful. That's why I always make you guys use the right variables. Because now I can use my triangle to find sine of theta, opposite over hypotenuse. So this is 1 minus x squared. And cosine of theta is x over 1, or just x. So I'd probably write this out as 2x square root of 1 minus x squared. And that would be my final answer. All right, that's it for notes, guys. Make sure that you re-listen to any parts where I went a little bit fast, or if you didn't have time to write it down, because we will be doing problems like examples 2, 3, and 4 in class tomorrow. All right, have a good night, and I will see you tomorrow.